Picture the entire universe laid out like a ledger, every star counted, every cloud of gas measured, every galaxy weighed. Now imagine that when scientists finally tally it all up, nearly half of what should be there simply refuses to show itself. This is not about dark matter, and it is not about dark energy either, though both mysteries loom over everything we are about to explore. This is about ordinary matter, the same atoms that make up you, your screen, and every star in the sky. For decades, roughly 40% of it has been missing. Galaxy clusters weigh less than they should. The gulfs between galaxies are emptier than the models predict. Either that missing mass is hiding somewhere we have not learned to look, or our entire picture of the cosmos needs rewriting. Then in the summer of 2025, astronomers finally found it, stretched out in plain sight, a filament of gas 23 million light-years long, connecting galaxy clusters together. Everything visible in the universe, every star, planet and wisp of gas adds up to more than 100 sexillion kilograms, yet this staggering figure is only a sliver of what should exist. Ordinary matter makes up just 5% of the universe's total contents. Dark energy accounts for roughly 68% and dark matter for about 27%, both invisible, both defined mainly by what we cannot detect. Even within that small 5% we can technically see. Cosmic microwave background measurements tell us 40% has never actually been located. The search for it stretches back nearly a century. In 1933, Fritz Zwicky noticed galaxies in the Coma cluster moving too fast for their visible mass to explain, and proposed a hidden form of matter he called dark matter. Decades later, Rira Rubin found the same pattern in spiral galaxies. Scientists began to suspect this dark matter and the missing ordinary matter might be hiding together, threaded along what is now called the cosmic web, a skeleton-like structure of filaments and dense nodes that has shaped the universe since its earliest moments. For years, directly seeing a filament proved almost impossible. Chandra spotted faint gas clouds in 2005. Hubble inferred one indirectly in 2012. In 2014, a quasar's light finally illuminated a filament directly for the first time. But these detections only captured cool ancient gas, not the hot diffuse material believed to hold most of today's missing matter nearby. That barrier fell in June 2025. A European team led by Konstantinos Mikas at Leiden University used Japan's Suzaku X-ray telescope combined with XMM Newton to remove interference from black holes and isolated a filament linking 4 galaxy clusters within the Shapley Supercluster. It stretches 23 million light-years, holds 10 times the mass of the Milky Way, and burns at 10 million degrees Celsius. It matched almost exactly what cosmological simulations had predicted. Now the European Space Agency's Euclid mission aims to map the rest of this hidden skeleton by around 2030. For nearly 30 years, scientists agreed on the universe's most likely fate: a big freeze where galaxies drift apart, stars die out, and everything cools toward absolute zero, driven by dark energy, a mysterious force discovered in 1998 when 2 teams found distant supernovae fainter and therefore farther than expected, proving cosmic expansion was accelerating. That discovery won the Nobel Prize and gave rise to our standard model of cosmology. But new results from the Dark Energy Spectroscopic Instrument DESI suggest dark energy might not be constant after all. Using data from nearly 15 million galaxies, the largest 3-dimensional map of the universe ever built, researchers found that dark energy's push may have weakened by roughly 10% over the last 4.5 billion years. If that weakening continues, expansion could eventually stop and reverse, ending not in a cold freeze but a catastrophic big crunch. The evidence currently sits around 4.2 sigma strong, but still short of the 5 sigma gold standard for a confirmed discovery. Meanwhile, a separate crisis is unfolding around the Hubble constant. The value describing how fast the universe expands, measuring it through nearby supernovae, gives a figure near 73.5 kilometers per second per megaparsec. Measuring it through the ancient cosmic microwave background gives 67.4. These two values refuse to converge, and every new independent measurement from megamaser galaxies to Mira variable stars keeps landing near the higher number. Skolnick, a Duke University physicist who helped lead recent DESI supernova work, has warned that our model of cosmology might be broken. One striking proposed fix published in 2025 suggests the entire universe might be slowly rotating once every 500 billion years, a spin subtle enough to hide yet strong enough to explain both values at once without breaking any known law of physics. And gravity holds one more surprise. While the universe expands, overall nearby mass can overpower that expansion entirely. It is why Andromeda is racing toward us instead of away. It is why our galaxy is being pulled along with everything around it toward a hidden concentration of mass called the Great Attractor, hidden behind our own galaxy's disk, its true scale only revealed once X-ray telescopes could see through the dust. Even that pull, it turns out, is dwarfed by something farther out, the Shapley Supercluster 650 million light-years away, holding an estimated 10,000 trillion suns worth of mass, drawing in everything within a billion light-years including us. All of it, the hidden filaments, the fading dark energy, the mismatched expansion rate, the invisible pull of the Great Attractor points to the same truth. We are still in the early chapters of understanding our universe, and every new discovery brings us a little closer to knowing exactly where and what we are.